Hello everyone, welcome to the second video in the series on the ultimate guide to studying physics. Okay, we're going to cover just selected topics, and in this video, we're going to be talking about the topic of gravitation and heat. Okay, so we're going to answer 4 questions on gravitation and on heat. Okay, so let's begin. 9.1 shows a rocket moving through the layer of Earth's atmosphere. Now, what is meant by escape velocity? Okay, escape velocity. Remember, the escape velocity belongs to the planet. It is the amount of velocity you need to escape the planet. Okay, so the escape velocity is very specific to that particular planet lah. And of course, in this case, it's Earth lah. But, in order to achieve escape, in order to escape the planet, whatever thing that is trying to escape must achieve that minimum escape velocity. I think understanding this helps us to know that actually when we calculate escape velocity, we are actually referring to the planet's escape velocity. So, dia macam syarat. Kalau kamu mau keluar daripada planet ini, kau mesti capai kelajuan begitu. Okay, so it is the minimum velocity. Okay, minimum velocity needed by an object on Earth's on a planet's surface, not Earth, on a planet's surface to overcome the force of gravity and escape. Escape where? Into space. I think this is the keywords, minimum velocity to overcome the force of gravity. Okay, in order to escape into space. So the minimum velocity is really different according to planet. Okay, in a way, the satellites, don't have its own escape velocity. There is, but it's very small. It's very easy to escape from a satellite. Okay, but something as big as the Earth with a very big force of gravity will have an escape velocity. Okay, that if you want to escape the Earth, you need to achieve this kind of escape velocity. Now, what are the factors affecting the escape velocity? The formula for escape velocity is V equals to square root of gm over r. And so you can see that the velocity is dependent on 2 factors, which is the mass of the planet and, of course, the distance from the center of the Earth. So these are the 2 factors. Okay, the mass of the planet. Okay, that's one. And then the second one is the distance. Okay, from the center, center of the planet. Okay, that's what the R is for, the distance from the center of the planet, not from the surface of the planet, from the center, because that's where the gravitational force is coming from. So I explained why the Earth can retain its atmospheric layer. Okay, so this is the same question and probably the same reason as why the rings of Saturn, the rings of Saturn over here, why is it that the rings of Saturn can maintain there? Okay, it's because the rocks or whatever it is that make up the rings of Saturn haven't gotten enough speed to escape to escape the planet of Saturn. So in a way, the Earth is the same thing. Okay, the escape velocity of Earth is high, okay, which is actually 11,200 meters per second. You don't have to remember the 11,200, but you just have to remember that in order to escape Earth, you need to achieve a very high escape velocity. Unfortunately, the linear speed of the air molecules, this is air molecules, okay, is not big enough to escape. The linear speed of air molecules is about 300 meters per second, which is fast, okay, but it's not fast enough, okay, to escape the Earth's gravitational pull. Okay, so it's a 2-mark question, so we're expecting a 2-point answer. Okay, now diagram 9.2 shows a communication satellite. Okay, and so of course when we talk about communication satellite, this is pretty standard lah. Okay, so we want the size of the antenna should be a big size of antenna. Okay, and usually big size antenna is so that you can receive or you can transmit more signals. Okay, better signal can be received, etc. Now, whenever we talk about communication, usually it's geostationary, and when you talk about geostationary, the reason is almost always one of these two, either above the same geographical location, or the second one is it is the same as the rotation of the Earth. Okay, it's very standard lah. Okay, non-geostationary, the reason is just opposite law. It is not always above the same geographical location. It can change the geographical location, or it is different. It can be different than the rotation of the Earth. It's faster or slower than the rotation of the Earth. And non-geostationary, usually we use for weather forecasting, to look at different places at different times. And geostationary is usually for communication, live telecast. That's kind of like, where we are going towards lah. And usually, I look at a lot of gravitation questions. Most of the time they ask about geostationary because it's an easier question. Okay, so you might want to think about that as well. Now, the number of solar cells obviously has to be more because the satellite is powered by solar energy. So the more solar cells you have, then you can collect more light energy lah. Okay, now a variation to this question is the size of the solar cell. Of course, you want a bigger size. A bigger size solar cell means you can collect more light energy, you can provide more power for the satellite. Now the mass, remember that this is a number, so you don't want to write the specific number, because if you're going to write 2000, then you're going to face a problem because K is 2000, but we are going towards J. So what do you write? You write low mass. Okay. Now for satellites, I know before this I said that if you say low mass, then you talk about, can achieve faster acceleration, or high velocity. Yes, that's true, but I want you to add a little bit more. Okay, having a low mass satellite uses less fuel during the launch. And because it uses less fuel, you are able to achieve whatever escape velocity that you want, okay, in a much shorter amount of time. You don't waste any fuel trying to achieve the escape velocity. Okay, so once you're done with that, then you will have the answer, J. Okay, don't forget the 10th mark. Okay, now a satellite with mass of 600 kg orbiting the Earth at height of 300 km from the Earth's surface. Calculate the speed of the satellite orbiting the Earth. Okay, speed of the satellite orbiting the Earth is the linear speed. Okay, 2 gm over r. Oh, sorry, I made a mistake. Actually, just now, escape velocity, escape velocity is not gm over r. Escape velocity is 2 gm over r. Okay, my bad. Okay, escape velocity is 2 gm over r because linear speed, okay, is gm over r. Okay, but okay, this one you need to be careful, and I would like you actually to stop and pause this video and try this question on your own. Now the r is very tricky. Okay, the r is the radius of the Earth. Okay, the radius of the Earth plus the height, okay, of 300 kilometers. So you need to find the radius of the Earth, r, okay, plus together with the 300, change the kilometers to meters. Okay, the value of the radius of the Earth, okay, r is equals to 6.37 times 10 to the power of 6 meters. Okay, so the r that we want, which is the distance from the center of the Earth to whatever satellite is 6.37 times 10 to the power of 6 plus 300 times 10 to the power of 3. Okay, so this is something that you have to be careful about. Now, the mass of the satellite, sorry, it's not 6. The mass of the satellite is 5.97. Okay, times 10 to the power of 24 kilograms. Okay, of course, G is very standard, 6.67 times 10 negative 11, totally not a problem. The one that, again, I said you should be careful is with the R. Okay, so once you've calculated that, you should get the answer. Okay, I'm just going to give you the answer over here. The answer for this, the answer for this is 2.4 times 10 to the power of 3 meters per second. Okay, the speed of the satellite orbiting the Earth. Now, the period of satellite orbiting the Earth is given by this formula, which is T equals to 4 pi squared r cubed over gm. Okay, again, the R, okay, again, the R is an issue. But if you get this correctly, you should get about 6.93 times 10 to the power 7. Substitute everything, you should be able to get 1.81 times 10 to the power 5 seconds, or you convert it into hours, you get 50.39 hours. Now, another way to do this is to use the formula T equals to 2 pi R over V. Since you've already counted the V, you can use this as well. The R is still the same. Okay, there are many formulas for this period of satellite. Okay, of course, the more popular one is 4 pi squared R cubed over Gm. Okay, and so this makes this particular calculation question a challenging one, especially if you're not familiar with the formulas. Okay, so I would suggest that you take some time, maybe you can pause this video for a while and work out the calculation. The answer that I'm giving you is the correct answer. Okay, it's just that getting the calculation over there may take you some time. Okay, again, if you really want to challenge yourself also, try to calculate the escape velocity. Okay, of course, it's not asked in this question, but you might as well practice calculating the escape velocity, and maybe you can write your answers in the comment section. I'll give you a comment back, okay, if you get the answer right. All right, let's continue with this next topic, which is heat. Okay, so 9.1 shows a clinical thermometer. Whenever you think about thermometer, you're thinking about thermal equilibrium, okay, or temperature. Okay, so what is the meaning of temperature? Temperature is the degree of hotness. Okay, degree of hotness of an object. Which is kind of funny when you think about it, because the unit for temperature is degrees. Okay, just as a reminder, since we're here, heat, okay, heat, the definition for heat is a form of energy. I mean, this is an acceptable definition at SPM level. Of course, there's a much more complicated definition which you can find in Google. Does not have to be mentioned here because this is, after all, only an SPM exam. Okay. Now, referring to the principle of thermal equilibrium and the working principle of thermometer, how can a doctor check his patient's temperature during the medical treatment? Okay, so of course, you start from where the thermometer is put and how does thermal equilibrium work, and finally what happens. I think a very important word that needs to be mentioned in thermometer is the fact that the mercury is expanding. Okay, so that has to be mentioned lah. Okay, so let's talk about this. Point number one, okay, will be that the thermometer is placed usually in the most two famous places, under the lip, under the tongue, okay, or under usually we put under the armpits, okay, of the patient. Okay, depending of, well, of course, there are other places to put it, but let's just put the two normal ones. Okay, so the heat is transferred from the patient to the thermometer, okay, which are in thermal contact. And this is usually a very important keyword when you talk about thermal equilibrium, okay, which is thermal contact. Of course, yes, the thermometer also transfers heat to the patient, but right now we're talking about the net heat. Okay, it looks like there's more heat being transferred from the patient to the thermometer. Okay, so the mercury in the thermometer, okay, expands when it receives heat. Okay, until the rate of heat transfer is the same. So whenever you talk about thermal equilibrium, these few words are kind of non-negotiable. Talk about thermal contact, talk about rate of heat transfer is the same. Okay, so when this happens, okay, when the mercury expands until it receives the heat, until it no longer has, until it has the same rate of heat transfer, okay, thermal equilibrium is achieved. Achieved, and the temperature can be read on the thermometer. Okay, of course, the temperature of the patient lah. Okay, temperature of the patient can be read on the thermometer, and that's how you would explain this particular question lah. Okay, now 9.2 shows the working thermometer. Sorry, that is not calibrated, has the length of 5.0. Okay, and 0 when this one, and then 25 when the temperature is 100. So the mercury column is LA, or L theta is 12 centimeters. Okay, when it is put into liquid X, because the question is calculate the temperature of liquid X, take your answer in unit Kelvin. Now the standard formula for this is that the temperature, temperature is equals to L whatever it is minus L0 over L100 minus L0 times 100 degrees Celsius lah. Okay, so the L theta is given as 12. Okay, so 12 minus 5 over, how I know it's 5? Because LO is 5. Oh, sorry. Okay, LO is 5. And then so 25 minus 5 times 100. Okay, and this will give you the answer of about 35 degrees Celsius. Of course, the unit is in Kelvin, so you need to add another 273 to this, okay, which will give you 308 Kelvin. Okay, so what is the length of the mercury column? Now they're asking for what is L theta when the temperature is 30 degrees Celsius. Okay, so 30 equals to L theta minus 5 over 25 minus 5 times 100. Okay, do this question and you should be able to get the answer. Hold on, 30 times 20 divided by 100 plus 5. About 11 degrees. Sorry, 11 cm. LCM. Okay. Sorry, about 11 cm. Let me just double check. 20 divided by 100 plus 5. Yeah. Okay, you should get 11 cm. Now, diagram 11.3 shows cross-sectional shape, etc., etc. for rice keepers. Okay, used to maintain the temperature of the hot rice. Okay, so you have 1, 2, 3, 4. Okay, now you are required to determine the most suitable rice keeper that can maintain the temperature of the hot rice for a long time and can be moved from one place to another quite easily. Okay, and so let's talk about the melting point. So the melting point, there's 240, 68, 68, and 240. Obviously, I think we want a higher melting point lah. Okay, why do we want a higher melting point? So that you can have, so that it doesn't melt easily. Okay, does not melt easily. Or the better answer will be to withstand, okay, high temperatures. Okay, this is the standard ones lah. Okay, then the next one you have specific capacity. So you have either 1,900 or 900 or 800 or 1,900. I think we would want a high specific heat capacity one lah. Okay, because we want to be able to keep the temperature of the hot rice for a long time. So it takes a longer time to cool down. Okay, so the reason for this is it cools, does not, you know what, let me write this. Okay. Does not cool down easily. Okay, or takes a longer time to cool down. Okay, because we want to keep the hot rice as hot as we can for a longer time. So we want it to cool down slowly. Okay, takes a longer time to cool down. Now, density, our choices are 670, 800, 800, and 670. Obviously, at this point, you kind of know that we're going towards the low density option lah. Okay, So we want a low density option so that, and as I said, I think in the previous video, when we talk about density, if it's low density, it will be lighter. Okay, lighter or low mass. Okay, and this helps us to move the thing easily. You cannot put this answer as your reason, but the reason why it can be moved from one place to another easily is because it is lighter, it is low mass. Okay, so of course at this point you kind of see that, okay, it's either L okay, or it's K. So I think the thing that differentiates this is the material between the inner wall and the outer wall. Okay, so our choices are either polystyrene or copper. Okay, obviously we want polystyrene lah. Okay, we want polystyrene, so our final answer will be L. Now, why do we want polystyrene? Okay, because it is a good heat insulator. That's a standard one lah. Okay, or it has a high specific heat capacity. There are many reasons for that lah. Okay, so I would put, because I just want a different answer than heat capacity, so I will put good heat insulator. Penebat haba, okay, a good heat insulator, so it keeps the temperature in for a much longer time. Okay, and so that will be L. Okay, L will be our choice lah. All right, let's carry on. This is the heat from Negeri Sembilan. Okay, so two spoons placed in a cup of the same mass, okay, cup respectively. Temperature decreases after a few minutes. This is very standard lah. Okay, so diagram shows temperature of time for both spoons. Okay, notice that the metal spoon reaches the set temperature at a faster time than the plastic spoon. Okay, so this is question number 11. Okay, so since this is question number 11, this is a modification question lah. Okay, so what is meant by heat capacity? Yeah, and so we find that with heat capacity, we're talking about slightly different thing. Okay, so heat capacity is the amount of heat to increase the temperature of a substance. Okay, don't put the 1 kg yet by 1 degree Celsius. So the amount of heat for this one for substance, okay, by 1 degree Celsius, that's heat capacity. Whenever you talk about specific heat capacity, then you have to put in the 1 kg. So the definition is almost the same, except that with the word specific heat capacity, the 1 kg must be included. Okay, so to increase the temperature lah, in that sense. Okay, so based on diagram 11.2, compare the final temperature, etc., time taken to become hot, and then rate of change of temperature, and then you have the two relations lah. So final temperature is the same, okay, because it reaches the same temperature, okay, at the end. Okay, secondly, the time taken to become hot, of course, the metal takes a shorter time than the plastic one lah. Okay, so metal is smaller than P, and then the rate of change of temperature. Now remember, rate is opposite with time. The smaller the time, the bigger the rate. Okay, so with rate, we're talking about the metal has a bigger rate of change of temperature than the spoon because it takes a faster amount of time. It takes a shorter amount of time to reach that final temperature. And so when you relate the specific heat capacity and the time of spoons to become hot, the bigger the specific heat capacity, the bigger the time of spoons, the bigger the time taken, okay, for the spoons to become hot. Okay, again, the specific heat capacity comes first. Secondly, specific capacity and rate. So since they are in opposition, the bigger specific capacity, okay, the lower, okay, the rate of change, okay, of temperature of the spoon. Okay, so this will be the answer for this one lah. Okay, so after an hour, the temperature of the coffee inside both cups are the same as the surrounding temperature. So I explain how this happens. So as always, this is obviously talking about thermal equilibrium. Okay, and so when you're talking about thermal equilibrium and this one, of course, what makes the question is asking for the coffee, okay, the temperature of coffee inside both cups are the same as the surrounding temperature. So the two things in thermal contact, okay, are the coffee and the surrounding. So be very careful with this. So the coffee and the surrounding are in thermal contact, keyword number 1. As mentioned in the previous question, coffee and the surrounding transfer heat to one another more heat is transferred from the coffee to the surrounding. Okay, then the temperature of the coffee decreases and the surrounding increases until thermal equilibrium is achieved when the heat transfer and the temperature are equal. And that's how the coffee becomes the same temperature as the surroundings. Now, what I appreciate about this question, you can take a screenshot of this. What I appreciate about this question is that it suddenly shifts from the spoons to the coffee. Okay, and so we find that, oh, okay, there's something interesting happening here. It's no longer talking about the spoons. Most people are suddenly, they'll go to automatic mode because previous question talked about spoons, so they think maybe it's talking about the coffee and the spoon. But no, we're talking about the coffee and the surrounding temperature. Okay, so be very careful when you're doing this. All right. 11.3 shows a container house. Okay, and obviously we have to talk about the container house being not suitable, etc., etc. What we want is to improve, okay, the ventilation of the house and to ensure the temperature inside the house is not high. Okay, so you want to have all this lah. And as I mentioned just now, one of the things that you have to talk about is the material for the wall and the roof. So you can also talk about the characteristic of the material, or you can talk about the specific material itself. Okay, and so here is a sample answer. Number of windows is high, obviously, so that you can have hot air escape more easily or more cold air can enter. Do not use the words ventilation in your answer because it is already mentioned in the question. Okay, so try not to repeat the question in your reason. Okay, the size of the windows is big, okay, so that same reason, more hot air can escape or more cool air can enter. Material of the wall should be a material with high specific heat capacity, okay, so that the wall does not become hot faster. Material of the roof is a heat insulator. You can also say high specific capacity, totally not a problem, okay, but I'm just giving you, a variety of answers to prevent the heat from entering the house. Okay, all this has to do with cooling down that particular container house lah. Okay, then we talk about paint. Because these are now additional features lah. So you use white or bright paints, okay, for this because it's a good heat reflector or it's a poor heat absorber. And then of course, a more famous one is you make holes, okay, on the upper part of the walls, okay, which we call air holes, okay, and so this enables the hot air to escape easily. Okay, so of course, there are many more answers than just this. Okay, but these are the most standard ones, and these are the ones that I found in the marking scheme as well. Okay, let's go to the final question of this particular video, which is the heat question from SMKA. So diagram 9 shows clinical thermometer placed under the tongue of a girl who has a fever. Okay, so same question as just now, but what is meant by thermal equilibrium? So this is a very long definition. So thermal equilibrium, when two objects are in thermal contact. Okay, keyword number 1 is thermal contact. Okay, heat is transferred between both objects. Okay, means from the object number 1 to object number 2 and object number 2 to object number 1. Never assume that heat travels one way only. It always travels both ways because thermal contact, okay, whether the object is hot or cold, always got heat transfer. It's just whether they are transferring more heat or less heat, okay, until the net heat transfer is 0. Okay, alternative to this, until the rate of heat transfer is the same. Either one of this is fine. Okay, I sometimes like to use the word net. Net is 0 lah. Rate is same. Either one also can, but the definition doesn't end there. Until the net heat transfer is 0 and they both achieve the same temperature. Okay, this is a very long definition. First, you talk about thermal contact, and then transfer between both objects, and then the heat transfer, and then same temperature. So it's a very long definition, which has 4 points to this definition. Okay, so it's not a very easy question lah. Okay, Now, based on the concept of thermal equilibrium, explain how the thermometer reads the temperature of the girl. Now, this is the same as the one that we did just now, lah. Okay, the one with this one. Okay, the thermometer, etc., etc., etc. So, I'm not going to repeat this again, but essentially it's the same answer. Okay, all the points need to be there. Okay, thermometer that has not been calibrated has a mercury column of length 28 when the temperature is 100. Okay, now the mercury column is 14 when put in liquid P. Okay, but the only thing about this question is they did not tell you about zero. What is the L0? This is L100. Sorry, 28 is L100. And then this is L theta. But the problem is they didn't tell you what is L0. Okay, so let's just assume that L0 is 0 cm lah. Let's just assume that lah. Okay, because there's not enough information in here. So, but if L0 is 0, then you get the temperature equals to 14 minus 0 over 28 minus 0 times 100, which will be 50 degrees Celsius. Okay, and so you can determine the temperature of liquid in Kelvin by adding 273 to this, so you get 323 Kelvin. Okay, so again, it's not enough information in this question to proceed, but let's just assume that L0 is 0. Okay, it's not good to assume now, but what to do? Okay, characteristics of the 4 types of thermometer. Okay, now again, there are 2 types of thermometer, okay, and there are 2 types of thermometer, and both types have different functions. Okay, mercury thermometer is a more standard one that can be used in like room temperature. Alcohol thermometer is more useful for very cold situations because the freezing point of alcohol is very low. Okay, so we need to look at the purpose of our choice. So the purpose of our choice in this particular question is the most suitable thermometer that can be used in the laboratory, which is in room temperature setting lah. So we're not going to the North Pole or the South Pole or Mount Everest where you need where you need alcohol mercury. Okay, so that's why we use alcohol mercury, like alcohol thermometer. Okay, we're going to use a mercury thermometer. Now, the standard answers for mercury thermometer are 2. One is, which is my favorite one, it expands and contracts uniformly. Okay, this is a very standard answer. And it's my favorite answer for mercury. Okay, but another one is it has a low freezing point. Okay, or a high boiling point. Okay, either one of these is fine. Actually, I like the high boiling point thing because we're working in room temperature settings. Okay, but these are the standard answers for mercury. Alcohol has a lower freezing point, so which is more suitable for like North Pole expeditions or things like that. Now, the glass wall bulb, the diameter of the capillary tube, the length of the thermometer, all talk about the sensitivity of the thermometer. Okay, so we want thin, okay, glass wall bulb. Okay, and why? So the glass wall bulb, okay, the wall bulb is this one, this one. Okay, sorry, hold on. Okay, this is the glass wall bulb. Okay, so we want this particular bulb to have a thin wall so that it can detect the heat easily lah. If it's very thick, susah kamu mau tentukan. So you want to sensitive. Okay, sensitive to heat change. Okay, diameter of the capillary tube. Okay, just to tell you, capillary tube is where the mercury goes in, this particular middle part here. Okay, so the diameter of the capillary tube should be small. Okay, and this is to increase the sensitivity of the thermometer. Okay, and of course, the length of the thermometer, at this point, you know that it's S already lah. Okay, length of the thermometer should be long. Okay, and the reason for this is to have a wider range of readings can be taken. Which makes sense lah. If your length of thermometer, if your thermometer is short, look at this, you can only detect from 35 to 42. Oh wow. Okay, so if a longer thermometer, you can read more, you can read more temperatures, like you can have more readings taken. Okay. All right. So that's the end of this second video. So in the next video, we'll discuss other topics lah. All right. Thanks everyone. Take care.